So my name is Karel Tels. I'm an associate professor here. So I have an assignment in education, but I also have an assignment in research. The research I'm focusing on is actually learning and adaptation in agent systems and robotics. We specifically look at nature and try to understand how they solve problems there, and then try to transfer it back to such an artificial system. And what we have seen in our recent research based on honeybee behavior is that we are capable in simulation to scale it far better, to more robots or to more agents than has happened so far. So that's why we now want to make the next step in bringing that to real robotics, try to see if we can have swarms of robots which are larger, which can solve maybe more difficult problems. What is so inspiring there is that this colony of honeybees consists of 40,000 individuals, but it's a completely decentralized system. There is not one boss who is saying to anybody what they should do. They are capable of organizing themselves. They are a self-organizing system. So if one of the honeybees falls out or drops out, the colony still functions. So we're trying to bring that principle to swarms of robots which are decentralized, self-organizing, in such a way that if one robot would, for instance, break, the entire colony would still function and would still operate to try to solve the task it was carrying out. So if you are thinking in terms of applications or even a more real-world application to robotic systems, then we could think of real-world settings like, for instance, a disaster which has happened. Take, for instance, Haiti, or take Chernobyl from a number of years ago, where you would not immediately want to invest people to go on this sarcophage to look for victims or to investigate something else. There we could think of dropping a swarm of robots which organizes themselves and go out and spread and coordinate and learn and adapt to the circumstances they find over there to locate different victims. When you drop an agent or a robot in a physical environment or the real world, such an environment is very dynamic. So a lot of different things can happen. And this robot or this agent must be capable of responding to that. So he must be able to quickly act. They need to be able to adapt to many circumstances, many different circumstances. And you could then think, okay, you could program such a robot beforehand and say, these are all the circumstances you can encounter, and this is the best behavior in each one of them. But that's simply not possible. There's simply too many possibilities. It's impossible for computers even to program something like that. So that's one of the reasons why it's important that they are capable of doing that. And also, of course, we would like to send out many. I mean, you could think of teleoperation, but that's not always that easy. For instance, if you send a robot to Mars and you want to teleoperate it, you have the delay in the signal, right? I mean, it could take about 10 minutes or something like that, I estimate. So, yeah, these 10 minutes can be crucial. So they need to be able, on these hostile environments, to act themselves. What we hope to achieve is that within 3 to 4 years we are capable of porting the smart algorithms, nice, elegant algorithms based on honeybees and ant behavior, to real physical robots. That is something we would like to achieve. And if we achieve that, then these robots are capable to coordinate for complex tasks like, for instance, locating danger or foraging for food or things like that.